I think I could teach an entire chapter in 28 minutes.
Maybe.
Not that you would ever understand it.
I would not challenge. I would sleep.
I would sleep.
This is only your second day with this teacher. I wouldn't challenge that.
I would sleep. Ah, the fun part.
I'm sick for tired.
Are you? That's horrible. This is Module 1, Section 3.
It's all relevant with itself.
Properties
One like
of logs.
I'd rather with you.
Now, because exponential functions and logarithmic functions are interconnected, there are properties of exponential functions. They are the ones that you're interested in. If you have a to the x times a to the y, I think we did this the other day, but these are the properties of exponentials. It's a to the
X plus Y.
x plus y. 2, if you have a to the x divided by a to the y, this equals,
Why are we doing this again?
shh, quiet. Just go with it, because it's related to logarithms in a
We just
way.
did this.
I'll show it to you.
X minus y.
So it would be a raised to the
X minus.
x minus y. The last one doesn't carry over so nicely, but it basically is a to the x. Well, you think about this one for a second. Well, it might be related to this one, but I doubt it. I'll try to think of a connection to
A
it.
to the xy.
A to the xy. Power to a power you multiply. If out of those three, the one you memorize is power to a power you multiply. So if it's not power to a power, the operation can't be multiply, so it has to be add or subtract. All right, so for logarithms purposes, we're going to look at the log of m times n. Let's call it log base b. I want to see if there's a way of manipulating this expression, the log of a product, where m and n are numbers that are larger than 0. Remember, they can't be negative, so m and n have to both be positive values. So what we're going to do is we're going to let m equal a to the x. We're going to let n equal a to the y. I'm just going to choose these as their possibilities. The nice thing about letting them be a to the x and a to the y is they're guaranteed to be positive, because exponential functions have to be positive for any value of x and y.
Yep. Let's begin.
You ready?
Let's begin.
Change this one into its logarithmic form.
Let's begin. Oh,
Get recorded. Future people will hear you.
cool.
So how do I change this into a log? No one will hear you.
Future.
She doesn't
Get
say
out while
anything.
you still can.
Get out while you still can.
Don't take this class.
Don't take this class online. That's what you should
Yeah,
be
so
doing.
take this class online. Take it with Cooler.
Yes. Uh-huh.
Accelerate.
Change it to a logarithm. 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 Focus. Focus. What is this as a logarithm? Oh, I'm sorry. Change A into B. I really meant that to be B. So B here and B here. I need the bases to be exactly the same. I got stuck thinking of exponential laws.
Yeah.
All right, change this into a logarithm.
Log base bx, right?
Log base B of m
Yeah.
is equal to x. And over here, this one is
Log base b
log base B of
n equals y.
n is equal to y. All right, those four things are going to allow me to break this down into something else. So the first step is to do substitution, where you see capital N, replace it with b to the x, where you see capital N, replace it with b to the y. So this becomes log base b of b to the x times b to the y. That's legal, because they're directly equal to n and directly equal to n.
So it's log base b of b raised to x plus y.
Therefore, the exponential laws. So log base b of b raised to the x plus y. Ooh, not big enough. What's that equal to? It's one little thing I left off, but you should be able to figure it out. What does a logarithm say in words? What power do you raise the base to get that answer?
What power do you raise b
To get b raised to the x plus y.
Wouldn't it be
Negative.
x plus y?
It would just be what?
X plus y.
X plus y. So the answer to this is x plus y. Another reasoning that we could have went is log and exponential functions are inverses of one another, and when they touch each other, they go poof. They just disappear. So this log base b and this b just all go poof, and you're left with x plus y. It's another way of looking at it, but most people don't like that.
That seems easier.
All right, well, yeah. The poofing, yeah, definitely much easier. What's x equal to now?
X is equal to log base b.
Log base bn. What's y equal to? From way over here.
Log base bn.
Log base bn. So we ended up with this, and we started with this. Therefore, those two things must be the same, exactly the same. So, law number one, log base b of a product. This only works for products. If there's a plus in there, you can't do this. If there's a minus in there, you can't do this. If there's division in there, you can, but you have to go through another law. This is going to equal log base b of the first one plus log base b of the second one. Is this helpful? Sure. For example, what if I wanted to simplify log base 2 of 8x? Simplify means you can write it in a different format so the numbers are either smaller or an easier to read format. So, is this a product, 8 times x? Yeah. So it could be log base 2 of the first one plus log base 2 of the second one, which is just x. Now, is that in a simplified form? I would say, heck no. It looks horrible. It looks worse than the original one. But, what's log base 2 of 8?
A squared. Or
Mm.
the three steps of that.
What is it? 3. 2 cubed is 8,
Yeah,
so
that's right.
this should equal 3 plus log base 2 of x. And therefore, it's an easier form.
Yeah.
Which one would you rather graph? This one or this one?
I don't know, they all look pretty.
I wouldn't graph either of them, I know. But if you were going to graph this one, it's the base function, log base 2 of x.
Just go up 3.
Take the graph and shove it up 3 units and you're done. But it's not very apparent from here what to do because that 8x is messing things up. All right, other properties. Doing the same technique, choosing a n equal bx, n equals by type thing, we can come up with the second property, which is this. Log base b of, m divided by n is equal to log base b of m. What do you think is next?
It's going to be minus.
It's going to be minus. Just like the exponential logs, division causes a subtraction. And log base b of n. So that gives us more options of what we can do to rip these things down.
Are we gonna have to memorize these?
Yes, there's only 3. This is the second one. So if you have a product, a log of a product, you could separate it into pluses, a lot of them. Log of the first one plus log of the second one, so forth and so on. If you have a quotient, one on top of another, the bottom one is always going to have a minus, the top one is always going to be positive. Third law, I'll do an example. What if I have log base...
This is an example of,
Yeah.
of this one right there.
To get to the third law. No, I'm going to do them all in one big fell swoop. Log base 5 of x to the 7th. Okay. I can break this down into log base 5 of x to the 3rd times x to the 4th. Is that legal?
Uh-huh.
I like doing this because it shows you other possibilities of looking at problems instead of as a huge exponent separated into smaller ones that you can recognize. Under law number 1, well, I can separate this product. You know, you have the times here. So it could be log of the first one plus log of the second one. So this would be log base 5 of x cubed plus log base 5 of x to the 4th. I probably shouldn't have used 7, but now that I've chosen it, I'm going to keep trucking through. What does it mean to be x cubed? What's x cubed? Well, I mean, what does it mean?
X times X times X.
X times x times x. I mean, simplistically, it's just 3 x's. So this would be log base 5 of 3 x's. I'm doing this in the longabout way. There's a quicker way. I just wanted to show the separation thing. Plus, what's log x to the 4th mean?
X times X.
4 x's. This is getting messier. Now, these are all products. So that means I can separate them all with additions. You know, products become additions. So this is going to become log base 5 of the first x plus log base 5 of the second x. How many of these am I going to have? 7 of them. So
Too many.
dot, 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 plus log base 5 of x. There are 7 of these. Great. Separate question. What's 3 plus 3 plus 3 plus 3 plus 3?
Say that again.
I mean,
3 plus 3 plus 3 plus 3 plus 3. Your question was,
5 threes.
how many times, right? 5. So the answer would be 3 plus 3 plus 3. Are you adding them? Are you sitting there going 3, 6, 9, 12, 15?
15.
What's the easier way to do it?
Multiply by 5.
Multiply by 5. So if I have log base 5 of x, 7 of them, what would be the final answer? I couldn't believe that. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll get there eventually. Oh, good God. So if there are 7 of these log base 5 x's, what would be the final answer? Just like 3 plus 3 plus 3 plus 3 plus 3 was 5 times 3, this would be
7 times
7 times
7 times log base 5 of X.
log base 5 of x. So what's cool here is we started off with log base 5 of x to the 7th. Where did the 7 go? It dropped down into the front. Out of all the laws, this one's the best. So law number 3. Log base b of m raised to a power is the same thing as a power times log base b of m. Why is that cool?
Because just put the
All you gotta
powers
do
in
is-
front.
Exponentials are hard to work with. Regular numbers are really easy. So we just took something hard to work with and made it very, very easy. That is the best law that you could be taught. This one right here. Now, how does it work? Well, we could talk about classically. You all have calculators nowadays, but when I was learning this stuff, we had to do it with tables. You ever seen mathematical tables? They're horrible. They're long, they're boring, beyond boring. Calculators, you type in a number, hit enter, and it gives you an answer. Tables, you would have to look up every little piece and combine those numbers together to get you your final answer. It usually would take about 3 minutes to solve a log of something, just a log of 101. And it would be really hard to find. On a calculator, you type in log 101, you hit enter, and it gives you a spit out answer. So these laws were always used to make things a little bit easier. Now there's higher applications for these, but let's start off with something simple. This is definitely on the test. It is one of my favorite test questions. Absolute favorite. If I tell you that log base b of 2 is equal to 0.25, log base b of 3 is equal to 0.37. I'm just making up numbers. What the heck? And log base b of 5 is equal to 0.86. Right. What I want to do is find log base b of 25 square root of 2 over 9. That's 9. That'll work. I want to know what this is equal to. Now, given the information on the left, I can find it. Is it going to be easy?
No.
Somewhat. It's not horrible. But it goes back to the 3 laws. If you see a product, you change it to the log of a sum. If you see a quotient, you change it to the difference of 2 logs. If you see a power, you put it out front. You just drop it down out front, which is totally okay. So, the first thing I need to do is, I see this 25, the 2, and the 9, and the only one that looks like something over there is the 2. What I have to do is change 25 and 9 into the numbers that are on the left. So how do I change 25 in terms of 2, 3, or 5? What is it? 5 squared. Because it can't change value, it's still 25, so I'm going to write it as 5 squared. So the first step is to go log base b. This is 5 squared times 2 raised to what power? What's a square root as a power? 1/2. 9, I can change to 3 squared. And therefore, I'm looking at a base of 5, a base of 2, and a base of 3, 2, 3, and 5. So they have all the right numbers. Next step, you use the laws of logarithms to make this thing as long as possible. It's called expanded form. So here's a product, so I can change it to addition. Here's a quotient, I'm eventually going to change it to subtraction. I try to think of it the easy way. Whatever's in the top stays positive, whatever's in the bottom changes to a negative. So when I expand this, it's going to be log base b of the first factor, which is 5 squared, plus log base b of the second factor,
2 to 1/2.
2 to the 1/2 power. And then the 3 is in the bottom, so this is going to become subtract log base b of 3 squared. So that's the first step, breaking in the numerator and denominator apart. But this, remember, this only works for products and quotients. If there's a plus or minus in there, all bets are off, unless they're contained within parentheses. Then you can work with it. All right, what can I do to the first one? Well, I can't solve it yet because this says log base 5 is at 0.86. So this one I need to do what with it?
Convert it.
How?
Take the 2 to the front.
Take the 2 to the front. So this is a power. By the law, this law up here, we can take that power and drop it out front. Just get dumped. So it'd be 2 times log base b of 5.
Which is 0.86.
So it'd be 2 times 0.86. The next one would be
1/2.
1/2 log base b of 2 minus 2 log base b of 3. And then do substitution. This will be 2 times a number plus 1/2 times a number minus 2 times a number. But when you put the number in there, don't put log. That's gone. Don't put the base b. It's gone. So where we see log base b of 5, you replace it literally with 0.86. So this is 0.86. The next one is log base b of 2. So log base b of 2 gets replaced with
0.25.
0.25. I love squeaky workers. And log base b of 3 is at 0.37. And now you can just type it in the calculator and get an answer. For a grand total of, I have no idea. Anybody figure this out?
Oh, I have a 1.105.
1.105? So this would be 1.105. So the answer to this original one would be 1.105. 5. Kind of cool, huh? So we took things that we knew and we generated an answer for something we didn't know. And these laws are really good about finding that. Of course, you do need to know a few things before you can start. But this is definitely one of my test questions. I guarantee it's on the test for this chapter, and it's also on the final. That's how much I like it. So a couple times. It's not bad once you know what you're doing. Log base b of a product is equal to log base b of the first one plus log base b of the second one. I don't know why I'm using capital A and capital B. I used M and N last time. It really doesn't matter.
Can I write my notes in pen?
I don't care. Just
I'm
don't make.
write
Well,
in pencil.
the danger with writing it in pen is I make mistakes. And then you start writing what I write, and it gets all messy. 2, if you have log base b of a over b, big A over big B, it's log base b of the first one minus log base b of the second one. Most people know what these laws are. It's just when I ask you to work with them, things fall apart. And I think the most important one, log base b of a to a power is equal to the power times that log base b of a. So today I just want to go through some examples of what to do with all this mess, or how I'm going to ask questions of you. So I don't forget anything, I'll actually look at my notes, which is rare. Boring.
Why can't we have those notes?
You can. They're, I think, not mine. They're not awesome notes, they're just so-so. While I'm there, I'll write a couple of the other properties. Simple ones. Not necessarily the main 3, but one of them is, what would be a good one? I just looked at it too. Oh, our conversion one. If you have log base b of x is equal to y, you can always change that into b to the y is equal to x. That one always comes in handy for many, many problems. What was one of the other ones? If you have log base b of b to the x, the answer is automatically x, because the b's are kind of like inverse functions. Similarly, weirdly written, is b raised to the log base b of x is also equal to x. Though very rarely do you see that notation anywhere, but it's very confusing. This one, most people are okay with, this first one. The second one, because it is an exponential that's really strange, log as an exponent, people don't see it perfectly. So the general idea is this. If these b's are touching each other, and it's, log base b of b raised to the x, they kind of just go poof. I call it poof. Canceling is usually inverse identity. Functions are a little differently. So here you have b raised to the log base b, and they're touching each other, so it just kind of goes poof, and you're just left with x. This is the inverse function property. All inverse functions, when you compose them with each other, will go poof. That's the beauty of inverse functions. All right. We already talked about common log and natural log. That's graphs of them. Oh, and it jumps right to that. I think I'm missing a section of my notes. Isn't that crazy? Graphs. I really am missing parts of my notes. Alright. So let's make up a few. I'm just looking in here to make sure I cover everything. I think I will. We did the decimal one last class, right? Where I had log base b of 2, 3, and 5.
Yeah.
Yeah. So let's do something a little bit not so nice. just get used to the language that's going to be thrown at you. When I say to expand this expression, what I'm expecting you to do is to break it down so that any common bases are gone. No multiplication exists between variables, no division exists, and no powers exist. So they all kind of get pulled apart. So the first thing to recognize is what operations are going on in the problem in front of you. So here, between the x squared and the y minus 3 is multiplication. So that can get pulled apart. The other thing that can get pulled apart is any exponent. You do that too there. So when we start breaking this down, if you want to do it like step by step, you would say log base b of the first one. I like using parentheses, I don't know why. Habit. When I say the word of, parentheses are usually around. And since it's multiplication, by log number 1, it turns into addition. But don't forget, you have to write log over again. You can't just write log of x squared plus y minus 3. That's not going to make any sense. It has to be a log of each factor. So it would be log base b of y minus 3. Can I separate log of y minus 3? Can I write it as log of y minus log of 3? No, don't think distributive property because that's not going on. None of the rules over here have anything to do with, on the inside, addition or subtraction. On the outside, sure, but not on the inside, so there's nothing you can do to the second part. What's the only thing you can do to the first part?
Bring 2 out.
Bring the 2 down, so you get 2 log base b of x plus log base b of y minus 3. And that's the best you're going to get out of expansion. Don't go too far, don't go too short. All right, let's make it worse. Log base 2 of x cubed cube root of y over 8 square root of z cubed plus 1. Why not?
Really?
I just want to show you, actually, this isn't any harder than the one above it, except maybe a little bit more writing. All right, so what's the first thing you want to write?
Log.
Log. Good, good, good. That's a good start. Log. At least say
That's
base
just
2.
Is that 2?
All right.
X to the third
X to the third
plus
plus
the log base 2
log base 2.
of the cubic root of y. Or you want to go ahead and break it down?
Now that's up to you. Do you want to leave it as the cube root of y?
No.
Because you won't be able to do anything with it.
Mhm.
What's the other way of writing it?
Right, putting the 1/3 in front of the log base of 2.
Not yet. I like doing things one step at a
Y
time,
to
but
the
eventually.
1/3.
Y to the 1/3.
Why wouldn't you put the, why wouldn't you put that with the first one?
Which one?
With the log base 2 x cubed.
You mean the y to the 1/3? You could. You could write log base 2 of x cubed, y to the 1/3, and then continue on. But eventually you're going to have to break it down because it's multiplication.
Okay,
Because every multiplication that exists has to go away.
gotcha.
Every division that exists has to go away. All right, so now we got the top taken care of. What about the bottom? What's that become automatically?
Minus.
Minus for each one of them. So it's going to be minus log base 2 of 8.
Plus. Would it be plus? Or would it
I'm
still
asking.
be minus?
Plus, I think.
You think
I think
plus?
plus.
This is multiplication.
Minus.
Minus. Why? Because it's in the bottom.
Oh, okay.
If it's in the bottom, it's automatically minus. Now, if I do put a plus here, I'm going to have to put a parentheses before that log base 2 of 8. But to get rid of the parentheses before you even get there, anything in the bottom is negative. Anything in the top is going to be positive. All right, so this would be log base 2 of How do you want to write it?
Whew. You have to put that z to the third plus 1 in parentheses
Z to the third plus 1 in parentheses,
and raise it to the 1/2.
and raise it to the 1/2 power. Square roots are half power, cube roots are third power, so forth and so on. All right. Can you do anything with the z cubed plus 1? Can you break it down? Even after you bring the 1/3 out front. Or, I'm sorry, 1/2 out front. No, because it's plus and minus, you don't care. So here we can drop the 3. So we get 3 log base 2 of x plus, drop the 1/3, 1/3 log base 2 of y. What about log base 2 of 8?
Shriek.
Shriek. 3. So it becomes minus 3. Nothing else. It's just minus 3. Because what power do you raise 2 to get to 8? Well, that's 3. And then finally, bring the 1/2 down. You get 1/2 log base 2 of z cubed plus 1. And you can't do anything with the z cubed. You're kind of stuck with it. So don't try to force that 3 down also. Is there anything else you could do to this without killing it? Yeah, that's done. There's nothing more to do to it. All right, so that's considered expansion. Then there's the other direction, which is considered contraction, or combining logs. So, screen here. I'll give you all the languages that are possible. Each and every one of these is saying to do the same thing. Contract it, which means instead of bringing it apart, you want to shove it all together. Combine your logs, that means if you have lots of logs, you want to write it as a single log. And then sometimes it'll just say literally write as a single log, or logarithm. All right, so log base 3 of x minus 1/2 log base 3 of y minus 1 plus log base 3 of
We have a visitor.
4 people. Minus 2/3 log base 3 of, I don't know, x plus 1. Alright, so if I'm going to write this as a single log, there's many different ways of doing it depending on your style. I was always taught to combine the positive terms and the negative terms so that the positive ones were close to each other and the negative one was far away. But there is a complete shortcut, but I highly suggest you take care of the powers first before you jump into the shortcut. So, where does this 1/2 go?
On the bottom.
1/2 power. 1/2 in front of a logarithm becomes
Exponent.
an exponent. You can't leave it in this position because you have to have just log out front so that we can go back to the laws of logarithms. So we're going to put the 1/2 back up, and I'm also going to change the way it looks. So it's log base 3 of
1
to the 1/2 power. What's a better way of writing that?
square root.
Square root. So I'm going to write the square root of y minus 1. I won't mark you wrong on a test if you leave it as that to the 1/2 power, but square root's just nicer. All right, nothing I can do to the log base 3 of z. What about the 2/3? What does the 2/3 become as radical notation?
The cubic root of
So log base 3 of the cube root of
x plus 1 squared.
x plus 1's quantity squared. The 2 becomes an exponent normal, and the 3 becomes a cube root. I wrote this poorly. That part a little bit longer. Does that make sense so far? I'll be asking you to do this in a little bit. All right, so now there's no numbers in front of each one of the logs. I can shove them together rather nicely. We can do it separately or all at one fell swoop. Which one do you want to do? Piece by piece or all in one fell swoop? I guess I'll go for piece by piece. If these two are the positive terms, that means they're going to get multiplied in the top, but technically they're going to be multiplied. So if I look at just those two, this becomes log base 3 of what? X times z. Alright. The next one, if you're going to do it piece by piece, becomes a little trickier. I don't like working with negatives, but if they're both negative, what can you do with the negative? It's a neat little trick from algebra. They have something that's exactly the same, what can you do with it? Oh, I'll write it a different way. If you have ax plus bx, can you combine those like terms?
Mm-hmm.
What do you have to do?
Bring the X out in front of the A.
What's that called?
I forget.
No?
Distributive.
It's the distributive property, but we usually call it something else. Begins with an F.
Factorization.
Factoring. So you would factor out an x. Well, these are both negative, so we can factor out a negative. So we can go minus log base 3 of the square root of y minus 1. When you kick out a negative, this becomes a positive. This log base 3 of the cube root of x plus 1 all squared. And parentheses. That's legal. And like I said, there's lots of different ways of doing this, of organizing it. I'm just showing you one possibility. Alright, now what? Well, I can take the ones on the inside because it's being, added and multiply those two as factors. So you get log base 3 of x times z minus log base 3 of what? Square root of y minus 1. Oops, minus 1. Times the cube root x plus 1 all squared. So addition turns into multiplication. I find that law better than the division one sometimes, but I'll show you a shortcut to this in 2 seconds. How close to the bottom? Alright, so this is one log, this is another log, and between them is subtraction. So what do?
Turn into division.
So this one stays in the top and the other one goes in the bottom. So you get log base 3 of x times z all over the square root of y minus 1 times the cube root of x plus 1 all squared. Not hard, right? It's just manipulation. Now, I don't do all that. Me personally, I look at it and write the answer in the next step. But it takes a little bit of practice. I highly suggest you at least do this line. Get that line down so your powers are out of the way and you only have individual logs. And if you look at what happens, the first one's positive. It ended up in the top, this x. The third one is also positive, and the z ended up in the top. The square root of y minus 1 was negative, or the minus of the log. It ended up in the bottom. And the same thing with that cube root one, it also ended up in the bottom. So you can put them in the right places. If they're positive, they stay in the top. If they're negative, they go in the bottom. But you could, go through all this little process to figure it out. Either way. Your turn. expand that one. You have exactly 1 minute. Should I set up Siri to time you? Tap there, make sure it works right. So, I hope at least you did this part. Log base 2 of 16 plus log base 2 of x to the third minus log base 2 of the cube root of y. What is a cube root as a power? 1/3. Alright, what's log base 2 of 16? 4, because it's 2 to the 4th. So this would be 4. What do I do with the 3? Bring it up front, log base 2 of x. What do I do with the 1/3? And you get 1/3 log base 2 of y. That's all you can do. And I'm writing very messily. Alright, try the other direction. Contract.
On that last problem, could I put negative log to y to the 1/3 instead of you paying 3?
But you don't want the 1/3 power up there. You don't want any powers, no multiplication, no division.
Okay.
Addition and subtraction you can't touch. And if there's addition and subtraction with powers, you can't touch that either. But if it's an individual thing to a power, you've got to make sure that goes to the front. 3 log base b of, I'm trying to think of a good one, x, minus 1/2 log base b of y minus 1, plus 4 log base b of z. So the first step is the numbers in front do not belong in front. They need to go up. So this becomes x cubed, this thing raised to the 1/2, this thing raised to the 4th. So you get log base b of x cubed minus log base b of y minus 1 to the 1/2, better yet the square root of that. We'll change it later. Plus log base b of z to the 4th. Now, positive things stay in the top, negative things go to the bottom. So as an individual log base b of, the top things are
X cubed.
x cubed and
Z
z to the 4th. So you go x cubed times z to the 4th over a half power is a square root
Of y minus 1.
y minus 1. And there's your answer. Ta-da. Isn't this easy? It is easy. Practice it. It's not that hard. Just feel the flow of these things. Logarithms and exponentials are the easiest things in the world. No matter what math you're in, they're generally the easiest things in the world. Ugh.
Keep telling yourself that.
I'm going to keep telling you that.
Okay.
Because you should get 100 on this test because it's so easy.
Okay, your test would never
If.
be.
So easy. If, I always put that little addendum in there, you do your homework. And you ask questions on the things that you don't understand still. And you might actually have to come in a little bit early to get help. That type of stuff. You should still get 100. All right. One last little topic in here, in this section. And we'll go back to this problem. We had log base 2, I think if it was 10 or 11 or 12 or something like that. It was something between 8 and 16. And I said, well, we don't know how to find this even using a calculator because the calculator is based on base 10 or base E. So there has to be a way of doing this. So one way of tackling it is to set it equal to x. And if you don't like the exponential form, you could always change it into, if you don't like logarithmic form, you could always change it into exponential form. So what's the exponential form of that expression? It would be 2 raised to the x is equal to 10. Okay. Now we're going to apply something to both sides. This will be strange. I'll kind of back up a second. If you have the square root of x is equal to 9, how did you solve that equation?
Square both sides.
You square both sides. You would apply the function square to both sides. If you had x squared is equal to 9, you would square root both sides, of course, then you'd have to add the plus or minus. So it's not a pure function change, but it's pretty close. So what I'm going to do over here is I'm going to apply a function to both sides, log base 10. I'm going to just apply it to both sides. So whatever you do to the left, you do the same thing to the right. So I'm just putting log in front of both of them on both sides. It's not times, it's applying a function, just like if you went up here and I said, I'm going to square both sides. That's applying a function to both sides. Here you would be square rooting both sides. So in this case, I'm just logging both sides. What can I do with the power there? Move it to the front. It's an exponential here, but exponentials under logs go out front. So this becomes x times log of 2 is equal to log of 10. Now, log of 2 you can type in your calculator. Log of 10 you can type in your calculator. So can I solve for x? How do I solve for x? Divide both sides by log of 2. And you get x is equal to the common log of 10 divided by the common log of 2. And you can type both of those into your calculator and get an answer. Now the answer should be someplace between 3 and 4. Here's the calculator. It should be between 3 and 4. Look at that, it's a calculator.
Why don't you let me use yours? Don't tell me the answer then at least.
No, I clear my memory every time. It should be between 3 and 4. What'd you get?
What is it on this
3, 2.
one?
Huh? What is it?
I got you,
LOG.
I got you.
Now be careful. Make sure you put that parentheses after the 10 and after the 2 so it works out. What'd you get?
3.32.
3.32? So x is approximately, it's not exactly, 3.32.
Now, how many decimals do you
2 should
typically
be
want?
fine. 2 should be fine.
Okay.
Now here's the problem with this answer. When you go back to the beginning, log base 2 of 10 represents what power do you have to raise 2 to get to 10? So what is 2 raised to the 3.32 equal to? 9.98? And then some other ugly decimals afterwards? 9.98. It's not exactly 10. And the reason it's not exactly 10 is you dropped off a lot of infinitely many decimals. So when you round numbers, it'll throw your answer off by a little bit.
Yeah, technically it's 99 because the third decimal is a 6.
Oh, is it?
it's
So it'd be
close.
9.99, which is really, really close to 10, but that still gives us what's called rounding error. So just expect that in your answers. If you're going to go check it, it's going to be a little bit off, just a little bit.
Okay.
If you want the exact answer, you have to leave it as log of 10 over log of 2. What are you laughing about now?
I said, well, I probably won't check them.
No, you probably wouldn't. You accept wrong answers.
And you get partial credit.
I swear. Alright, so to prove it, that this is going to work and come up with a nice little formula, the way you do it is don't use any numbers at all. So you start off with log base b of a. Log base b of a. Where the base can be anything, the number can be anything, but we're going to start it off the same way. Let it equal x. What do you do to both sides? Oh, what do you do to it first before you
Bring
do
the
it?
A out.
No.
No, never mind. You would do
Compare it to the one we did over there.
bx. Would it be b?
B raised to the
x
x is equal to
a.
a. And then what?
Then you do log.
Of the left
Yep.
and log of the right. What goes inside the parentheses? Well, b to the x. And over here,
A.
a. So you're just applying log to both sides. Then
To
what?
bring the x out to the front, so x times log of b equals the log of a. Divide both sides by the log of b. And the calculator doesn't give you that answer.
No, but it does give you a way of avoiding all of this work.
So x,
You can jump down here to the end now.
so x equals log of
A over log of b. Log of the number over log of the base. So, for example, if I'm trying to evaluate log base 7 of 57, what's it equal to in a calculator? This is called the change of base formula. Change of base. Change of base formula.
You can.
So how would I find log base 7 of 57, approximately? What would I type into the calculator?
I don't know. That's what I was
According to that formula,
Log of 57
log of 57
over log of 7.
over log of 7. And that's it. And it gives you something to answer. It'll be 7 point something. 7 point something? No. Can't imagine it's 8. No, can't be 7. I'm thinking multiplication. Shh, quiet. I was thinking multiplication. It's powers, powers. All right, how about this one?
2.08 is option.
Log base 12 of 10. Type that one in your calculator. What do you have to type in?
Log of 10
Log of 10,
over log of 12.
and your answer is?
0.93.
0.93? It's less than 1. Why is it less than 1?
Because your denominator is greater than your numerator.
Well, over here, but over here your base is smaller than the number you're trying to obtain. Can I ever make this negative? Can the log of a number be negative? Can the log of a number be negative?
Obviously, yeah.
Obviously, yeah. So let's find out when it'll happen. Log, what would be a good one? Nah, that won't work. Log base 3 of 1/5. Log base 3 of 1/5. So to type this in your calculator, you'd write?
Hold on now. Let me catch up to you. Trying to make sure you don't make mistakes, so I have to erase.
Who, me? No.
So you would type in the log of 1/5 over the log of 30, right?
Mm-hmm. And the answer is? Negative. Negative 1.36?
46.
46? Negative 1.46. And the reason it's negative is to change a base of 3 into something smaller, fractionally smaller than it, you have to go into the negative land. Negative land. I'm really surprised that that wasn't possible.
Are your that's multiple choice, I can't remember.
Multiple what?
Yeah, I hadn't.
Multiple choice?
I didn't think so, but I was just
Oh.
curious.
Multiple choice is great for teachers because it's easy to grade, but you can guess and get the right answer, and there it throws me off thinking you know something when you really don't. My son could pass a multiple choice math test, but if I asked him to do something in math, he couldn't do it. Of course, he never asked me for help. I wonder
Probably
why.
either.
My own children are scared of me. Or don't want to deal with me. One of the two.
Because they want you to be straight to the point and show them how to do it and don't keep talking.
No, they just want to know how to get to the answer and forget all the why part of it.
Right, that's how I'd be too.
I know. You think I don't know that? I know that. I can tell.
Show you how to do it.
So one weird thing is if we have log base 7 of, what was that first one? 57?
Is this another example?
Just another flavor. It's going to come up with the same answers, but I want to show you a different method of doing it.
Okay.
Let's say we get it all set up, so this would be 7x is equal to 57. Is log the only log that brings things down? The powers, is it the only function that brings powers down? Log. The answer is no. You can have log base 2, log base 3, log base 7. What's another log base that's important?
10.
10 we've covered over here. What's the other one that's important?
Is it E?
E. Log base E. How do I write log base E quickly? ln. So what you can do to this is write ln on both sides. I like ln better. The reason I like ln better is this. How many letters are in ln? How many letters in log? I'm that lazy. One letter shorter is better. Of course, same thing goes inside here. So you get this and you get this. Drop the x and divide across, and you get x is equal to ln of 57 over ln of 7. Now what's cool about this is generally if you do different functions top and bottom, your answer is different. For instance, the square root of 5 over the square root of 3 is not equal to the cube root of 5 over the cube root of 3. That's definitely not equal. Absolutely true. But ln of 57 over ln of 7 is the same thing as log of 57 over log of 7. It is one of the weirdest functions that it allows you to change the function, but the answer stays exactly the same, which is kind of cool if you think about it. I can't think of any other function that does that where you can split it and the answer stays the same when you change it from one base to the next. I guess would probably be the easiest way to say it. So another change of base formula would be log base b of a is equal to ln of a over ln of b. I like that one better personally. I'm not sure if the book covers that one. Yeah, they do. They just show them as two separate laws. One topic that's not in the book that we still should be able to deal with. I think. We'll find out. So, maybe not in the book. If it's in the book, it might be further on than where we are right now. But this will allude to some of the things I'm going to teach you later on, one way or the other. Change any exponential into any base. Of course,
Shouldn't it be may not be in book,
may
not be
quiet.
in book? Sounds
Maybe
like
not in
somebody
book.
else needs to be in
May
the library brain.
not. It makes sense. Maybe not in the book. That's the way my brain works. Change any exponential into any base. We usually want. Oh, I can't even spell. Now you got me all flustered. E. We usually want to change the base into e, because the function with base e is the natural base, natural function. And it makes life a little bit easier. So here's how you start. Let's say we have 7 to the x is equal to something. Well, 7 to the x is our function. What we want to change it to is a function in base e. So I want to change 7 raised to the x power into e raised to the a power. 7 raised to the x power equals e raised to the a power. So what I'm trying to solve for, to find, is what the heck is a? Because once I find a, then that equality will be fixed. So this is a little strange, but it works. What can I do to both sides? I can ln it, just like over there. I can ln both sides and see what happens. I can backtrack it and change it back into something else, but it's easier from here. So ln both sides. So we get ln of 7 raised to the x is equal to ln of e to the a. Okay. What happens on the left-hand side? The x comes down. So you get x ln of 7 is equal to. What happens on the right-hand side?
That L and E cancels out.
Why?
I can't remember why, but I know it does.
The ln and e go poof because they are
Side by side.
not equal.
They're reciprocals.
Begins with an I.
Inverses.
Inverses. Because they're inverses and they're the exact same base, they go poof, and what you're left with is a. We wanted just to find a, and we just found a. A is equal to x ln of 7. So if we want to work with this function, we can say it's 7 to the x. That's perfectly fine. But it's also e to the x ln of 7, which in calculus language is much nicer than 7 to the x. Finding answers with 7 to the x is really hard. Finding answers with e to the x is very easy.